Okay, right. So let's get started. My sincere apologies for a bit of a late arrival here. It's nice to see everybody. I'm glad to see that you're all back in lecture today. And now we're finally going to start the geometry part of this geometry course. We've got a little bit of advertising material out of the way, followed by some linear algebra preliminaries. But today, I think really, unless you've taken a geometry class in the math department, is likely to be new material for most of you, which is fantastic. In terms of announcements, again, your first homework is due a week from Wednesday, apparently, which is great. So be sure to get an early start on that. And there's also, remember, these weekly engagement things, which are not intended to take more than like maybe 30 minutes to an hour, but they are just things to kind of keep up with this class, right? So it's like read a paper and report about it, or chat on Piazza or something like that. And I believe Thea already put a submission thing on the course website on Canvas, so you can submit that anytime. And another quick reminder to just take a quick glance at the project instructions and have that in the back of your mind. You might as well be thinking about that as we think of the technical content in this course. Any questions about logistical stuff before we get started? Yes, Thea.
There are going to be office hours starting today in this room right after class.
Oh, yeah, that's right. So we finally got office hours reservation. So they'll be here. Thea will be hanging out. My office hours are on Wednesdays, 10 to 12. So every day after class is for an hour, I think. And then we got 2 hours on Wednesday. So more than enough to cover all, you know, they're always, we choose the hours strategically because we know you don't do your homework till the day before. Any other questions, comments, concerns? Favorite recipe? Interesting news events? What was that?
She made bread.
Made bread. Mazel. Okay, so today we're going to be talking about curves. This is going to be the topic of our lecture for today and Thursday. Today is Tuesday. Yes. So in these two lectures, we're going to talk about the differential geometry of curves embedded in 2D and then curves embedded in 3D. And this is largely to just get our brains thinking like geometry brains. And in particular, we're all used to thinking about calculus and doing integrals and derivative and all that kind of math. And that certainly is going to be the basis of a lot of the models and the computations we'll do in this class. It turns out like calculus is a useful branch of math, despite what you might remember from math class. Everything good, Kartik? But in order to apply calculus to geometry problems, we need to do a little bit of adaptation. And so we're going to talk about the kinds of themes that it takes to turn like differential equations into differential geometry today. And just starting by discussing what it takes to define a curve in the plane and in 3D and compute its curvature and understand how to characterize a curve up to rigid motion using tools of calculus, but by kind of quotienting out the parts of calculus that are relevant for geometry. That's going to be the theme for today. Okay? So the sort of first question that we should ask, at least sort of philosophically here, temperature warning. Huh. Okay, folks, so those of you who are sitting under the projector, if any flames come out, I encourage you to scoot away. Right, so essentially the question that we're going to begin by our discussion in this course by asking is, what is a curve? I mean, we all talk about curves in calculus class, even algebra class in high school. But when we talk about the term curve, we have this kind of informal picture in mind, like this little purple line here. And it's actually a little bit trickier than we might think to define a curve, and in particular a differentiable curve, in a way that makes sense for, again, geometry rather than just calculus. Right? So when I use the term curve, I have to be quite careful. Like, what do I mean? How do I formalize this object? Now, the initial temptation, and I think the one that you probably remember from like pre-calculus class, might be to do something like the following. I could say, well, what is a curve? It's really just a function from the real values or some interval therein into the plane, if it's a plane curve, right? And then maybe the curve is the image of this function, right? That feels like a reasonable definition. And you are all nodding, which is great, but you're wrong, right? So in particular, I mean, we have this nice, very friendly looking schematic of what we think a curve looks like for a generic function here, gamma of t. But here's a counterexample, which is the following. So here's gamma of t. By the way, when we have this triple equal sign in this class, it's going to mean like is equal for all t, like it's equal for a lot of different inputs. That's kind of how you read that extra thing here. What is this gamma? Is this a curve? No, we're shaking our head. What is it? Yeah. Thanks, Marcel. It's a point. Right? So this is the origin. If you'd like, I can draw it for you. Done. Okay? Oh, sorry, I forgot my axes. I got yelled at on YouTube for that. Okay. So, right. So would we consider this thing a curve? Probably not, right? So it's not enough to just talk about functions from a line into the plane and say this thing is a curve. And indeed, later on when we talk about surfaces and manifolds, we'll run into a similar restriction, right? This is going to be a problem. Does this make sense? We all agree so far? I don't think I've said anything too complicated, right? This is a zero-dimensional object, not a one-dimensional object. Okay. So let's start to, so suddenly there are like cracks appearing in the facade, right? Like the calculus tools that we'd like to use are already getting a little fishy. And indeed, there are a lot of different kind of counterexamples that we can cook up that make us think that calculus isn't the beginning and end of geometry, which is not entirely surprising, but is worth pointing out. So here's another example. We've got this little green guy. He's driving along the curve y equals 2x. I chose it because I found this nice handwritten picture on Google. And here's a really interesting pair of functions, gamma 1 and gamma 2 of t, right? So here t, I think it's totally reasonable to think of t like time, right? So at a given time, t is like the position of the car. So he's like driving along. And then I think our intuition for what a curve is it's kind of like, you know, if there were exhaust coming out of the back of the car, it would be kind of like the shape that gets traced out by the exhaust. Yeah? Does that make sense? Exhaust, I guess, is at this point kind of a dated way to explain car driving. But in any event, here are two different functions gamma of t. The first one very clearly traces out this curve here, right? So like here y is 2 times x. Yeah? Now what about the second function? What's happening here? So when t is less than 1, maybe he's following the same curve as gamma 1. And then at t greater than 1, we follow this other thing. And if you check this thing carefully, you'll notice that still y is 2 times x, right? So concretely, what's going on in this choice of gamma is that my guy, he's driving along on the road, right, on this very vertically sloped road, and suddenly the time hits 1, he jams on the accelerator, and the car drives 2 times as fast. That make sense? Are these the same function? No, as a function of t, these are two different objects. But I would argue these are the same curve. Right? And so this is going to be the kind of thing that we're going to have to worry a lot about when we do differential geometry, is we're going to apply calculus to functions. That's perfectly fine, but then we're going to have to be careful that if two functions happen to give the same piece of geometry, that they give the same output when I do calculus on them. Does that make sense? Fantastic. And this is the kind of thing that we have to be careful about. Yeah? Now, moreover, differential geometry is an area where we're applying calculus to geometry, so it seems useful to apply derivatives. And we have to be really careful what it means to be not just a curve, but also a differentiable curve. So let's think of a counterexample there. So this is my job today is to give you lots of just little corner cases to think about to make sure that you're checking all of your calculations carefully in this domain. So here's a question. Let's say that I have a gamma that traces out a curve, right? And I want to know if my curve is sort of smooth looking, like it's differentiable. We'll formalize that in a minute. Is it enough to think of gamma as being a differentiable function of t? We're shaking our head. Why not? What could go wrong?
Sorry, I can't think of
That's okay. You knew I was asking the question, so the answer must be no. Yeah, that's totally reasonable. Yeah, Artur.
Maybe if I understand correctly the question is if the curve is smooth, but can gamma be non-differentiable? I guess if we can jump with the same curve, but we jumped somewhere that came back.
Yeah, so Artem is asking sort of the opposite question, which is if my curve is smooth, does my gamma have to be smooth? And the answer is certainly not. I mean, this is an example where it's not. What about the opposite of that? If I have a smooth-looking curve, right, is that, or rather, if I have a smooth-looking function gamma, sorry, does my curve have to be smooth as well? Here, somebody new, or either one. You spoke first.
Y is not differentiable with respect to x or something at a point? Like you can have a cusp or something?
A cusp, that's a good intuition. In particular, there's this weird variable t here, like time. And notice that time has no effect on the shape in a sense. It's just a byproduct of how we're writing curves down. And in particular, here's something that my car could do. I can drive along the road, come very smoothly to a halt, and then like back up in some other direction. We've all encountered cars that do that. If you're in my car and I'm parking in Somerville, it happens a lot. And so, right, here's an example of what can go wrong, and indeed cusp is exactly the right word. So here's a very innocent looking function gamma of t, where the x-coordinate is t squared, the y-coordinate is t cubed. Hopefully we all agree that gamma as a function of t is differentiable. Yeah? However, I think we would also agree that this is not a differentiable curve. There's a cusp here. There's like some lack of derivative that happens at the origin, right? And if you kind of check what's going on, what is the derivative of this? It's 2t comma 3t squared. So at t equals 0, the car basically comes to a halt for like a little minuscule second and then backs off in another direction. And so like, if you're a passenger in this car, you're not like experiencing wild forces, but you still manage to trace out an object that has a sharp corner. So these are the kinds of counterexamples that when we're doing differential geometry, we need to be super careful about. There's some interface between function and shape, and it's not entirely obvious precisely what it is. It's also not super complicated, but it is something we have to be careful about. That make sense? Any questions so far? Fantastic. And obviously, if you're sort of anticipating what we're going to do next week, surfaces are going to have exactly the same issues, but now we can develop kinks in all kinds of different directions, as they say. Yes?
I guess you're talking about differentiability as this sort of intuitive thing where like cusps are like rejected.
Right.
But like, I'm still not sure why that's a problem. Like, what if the derivative just is 0 there? Like, I mean, I can see visually that like that's a problem, but it's not clear to me in the math like why like maybe 0 is a fine derivative.
That's right. So we're going to have to add some detail before this really matters, right? I haven't given you any equations yet. But the basic issue is going to be, for example, what would be the curvature at this location? Well, it'll probably be like infinity, right? And so a lot of the formulas that we're going to write down are going to break down in this case. And we're going to be very careful to sort of only work with smooth-looking objects, which we'll formalize momentarily. Yeah, that's a fantastic question. And to make matters even more complicated, in our next lecture, we're going to talk about polygonal curves, because that's what we can do on computers. And that's sort of exactly the opposite of this situation, right? Everything is a cusp. Yeah. Any other questions? My job is to confuse you at the beginning, and then we slowly deconfuse until the next lecture where we throw in even more confusion. Yes?
So will we ever give a definition of differentiability for like a curve?
No, it's secret. Yeah. No. Yeah. That's our next task in lecture. Absolutely. Okay. So thank you for the fantastic question, which leads us to ask: so what is a curve? So first of all, we're doing geometry in this class, and when we talk about a shape is not a function. A shape is like a set of points. Do you guys understand the distinction? That, like, for instance, there are multiple functions that define the same curve. And so when we use the word curve, we're really thinking of that picture that we're like drawing in the plane. And this is the thing that we have to be a little bit careful about the distinction. There's clearly a relationship between these two notions, but we need to be careful exactly what it is, right? And to go to your question, yeah, our task here is to formalize exactly what that means. Sound good? And this is really a philosophical thing. Now, if we want to dig in a little bit more detail, phone is going crazy. We did a practical joke on a friend and it got a little out of control. Let's try and define curve specifically. And now if you look in the world of geometry, usually we think of a curve as an object that kind of locally looks linear, right? Or sometimes we say locally one-dimensional. So in other words, like, let's say I have my magnifying glass and I bring it closer and closer and closer to this curve object, right? Eventually, it kind of just looks like a little straight line, and then we can apply the tools of calculus to it. Notice, to go back to your question here, if I have this cusp shape like we drew before, no matter how small I make my magnifying glass about that cusp, it's never going to look like a straight line. It looks like a little angle. Does that make sense? This is a convention. I mean, like, it could be that you want to consider shapes like this, and there's certainly people who do. But in computer-aided design, this kind of geometry is wildly important. But for now, in differential geometry, we're only going to consider smooth objects. Okay, so how do we formalize this? It's a little bit tricky to get the schematic exactly right, but this is a definition you may have encountered before. So, let me get my notes here. Right, so we have a curve. And again, remember that a curve is a set of points, and maybe just to be generic about it, we'll say it's a set of points in Rn. The ambient space is not going to matter a whole lot for the definition. And essentially what's on the board is the schematic for how to understand the definition of a curve. So, in particular, oh, the eraser's hiding over here. What are we going to say? Well, let's say that our curve, let's give our curve a name. So we'll say C is our curve, right? And remember our definition. It says that like I can take a little magnifying glass and in some tiny little neighborhood around every point on my curve, it looks like a line. That makes sense? So in particular, the first thing I have to do is to choose where I'm going to point my magnifying glass. So we're going to give that point a name. We'll call it P. Yeah? So let's say for all P, this is going to be on the slide in a second, so I'm going to be lazy about writing down all the words of the definition. We'll say, OK, for all P in my curve, there exists an open neighborhood U, which contains P. Right? Hopefully you can read my terrible mathematician handwriting. That's why I try to be careful about reading it out loud as I write it down. So I choose a point P on my curve. And for any P, it can be a different neighborhood U for each P. But for each one, there exists a neighborhood U so that if I take the intersection between C and U, right, it's given by the some gamma, oh, oops, I said gamma and I wrote G, but some gamma of like some interval, like, I don't know, A, B, like that, where gamma is going to go from like A, B into this curve. So it's like the image of a unit interval. Now, so far, I haven't discounted that cusp case, right? Like, because it could be that this guy is pointy or 0, right? That would be a problem. So if I have a differentiable curve, I'm essentially going to make gamma differentiable. You could also talk about a non-differentiable curve in metric geometry, but we're not going to worry about that here. But I still haven't discounted the cusp, right? So in order to do that, I'm going to have gamma prime not equal to 0. So in other words, once my car starts driving, it can't stop. So let's make sure that we can parse this definition. And I have it on the board in a much tidier way, because this basically makes no sense the way I've written it. So essentially, what is it saying? A differentiable curve is a set of points. That like little first part of this definition is the key one. A curve is a set of points. It is not a function. Yeah? So it's a set of points with the property that for any P, there exists a neighborhood U around P. So like, again, I choose a point along my curve. Here it is, P. And then I'm going to like draw some little blob around it, like that. So that the intersection between my curve and that open neighborhood, so like in other words, I'm just going to like cut out this little piece of my curve, looks like the image of some function gamma with the property that gamma prime is not equal to 0. Does that make sense? Now you have to be really careful when you read definitions like this, right? There's a lot of for all and there exists. It could be that like gamma is non-unique, right? Like it could be that multiple cars can drive down the road at different speeds, essentially is the way to put it, right? But it's saying that at any point on this object, I draw a little ball around that point, and it looks like the image of a function that never degenerates, namely that the car never grinds to a halt. And it turns out that is enough to prevent this cuspiness from happening. Any questions about this definition? Yeah?
Are multiple curves a curve?
Come again?
Are multiple curves a curve?
Oh, that's a fantastic question.
Is that one curve, or is that?
Yeah, so for instance, let's say that I have two intertwined loops like that that are not actually tied together.
Separate,
Sure.
or like concentric, or
Yeah, so like two concentric circles? Yeah, that satisfies the definition. Absolutely.
so you would call that like a curve?
That's a curve.
Okay, cool.
By this definition, yes. If you added the word connected, then it would not be. But and depending what textbook you use, maybe they do, maybe they don't. But remember that we're doing differential geometry, which means that all the calculations we're going to do really are going to involve little itty neighborhoods around points. So the fact that there's this global stuff here is actually kind of irrelevant. Now later on, we're going to talk about winding numbers, and there you will need it to be connected, right? Or it's not going to make sense. Yeah. Other questions? Yes.
Do we need different local parameterizations to agree on the intersections of the
Absolutely. Yeah. So so the question was like, like what if I have two different functions? You're right. They all need to trace out the same curve, or you can check that it won't satisfy this definition. But this definition is a little sneaky, right? It says the curve is a set of points with those parametrizations. Some old school differential geometry textbooks do it a bit differently. They say a curve is a set of functions gamma. I think that's a lazy definition, personally. Yes?
This also like enforces global bijectivity, right?
Global bijectivity. Well, it doesn't say it has to be the same gamma for the whole object. Right? It just says there's, like, I can always take scissors to every little piece and get a gamma. However, it's a fantastic question because there's a different object called a parametrized curve where there's just one gamma that traces out the whole thing. And so long as gamma prime is not equal to 0, you can check there are no kinks. Okay? However, you have to be a little bit careful because, like, a parametrized curve you usually do think of as a function gamma, but multiple functions gamma could trace out the same object, right? So you just have to keep that in the back of your head when you work with this object. Now, in 2 dimensions, there's an equivalence, right? Like, every curve is a parametrized curve, just by virtue of topology being easy in 1D. In higher dimensions, that's no longer the case. In other words, like let's say I have a sphere. There's the universal mathematician drawing of a sphere, in case you forgot what it looks like. You know, or even worse, actually, let's say I have a torus, like a donut. There's not going to be like a single thing that maybe covers this without like a lot of overlap between different pieces of your function, right? So there it might make sense to like cut this into different parts and parametrize each one separately. But we're not there yet. Yes?
Sorry, why would every curve be a parameterized curve to like the example of concentric circles? That's an unconnected.
Oh, sorry. Yeah, every connected curve is a parametrized curve. Yep, you got me. Any other questions? Yes?
Why are we allowed to have it overlap itself? Because if you zoom in on the actual point of intersection, it's going to look like a little X.
Ah,
right?
that's a fantastic question. So this object is not a curve. This is a parametrized curve, but it's not a curve.
Okay.
Because I've attached this function gamma, I've sort of disambiguated the 2 crosses in this X. You're absolutely right. Right? So this thing it satisfies the definition here that this is a set of points traced out by a function gamma whose derivative is non-zero. But it's not strictly, in the sense of the previous slide, a curve. Yeah, that was the sentence I was missing before all these questions came up. Fantastic. Any other questions? Yes?
This figure, like the curve has, or the parameterized curve has like an endpoint.
Mm-hmm.
Is it just because it keeps going off the slide, or is it okay for a curve to
That's a fantastic question. By our definition of a curve, there are no endpoints. Right? Because every single point on that set needs to be the image of a line segment, right? So if you think about this definition here, right, if I have a curve that comes to a stop, and I draw my open neighborhood around U, my open neighborhood U around that endpoint, notice that no matter how small I make that endpoint, it's never the image of an open interval. It needs to be the image of a closed interval. If you want to have a curve of an endpoint, I suppose you could like erase the very endpoint of the curve to try and make it kind of the image of an open thing. I think we typically don't worry about that case a whole lot, but actually in differential geometry, that's perfectly fine, because that means at every point on the curve, there does exist a little tiny neighborhood that just gets smaller as you approach the boundary. Yeah. Mm-hmm.
This sort of implies like we can only have countably many maps onto the curve.
It most certainly does not, but we'll come back to that later. Accountability is an interesting question, but that's a challenging one. The curve is closed. The set of maps, you have to put a topology on that. Is not the same thing. Yeah, would be my mathematician answer. Any other questions? You guys are holding me to account today, which is fantastic. Okay, cool. So let's add a few terminology, piece of terminology that you might encounter. If you have a parametrized curve, the object which is its image, which would be the thing that we hope is a curve, is called its trace. Notice that the trace of this is a curve so long as it doesn't intersect itself, to go back to the question from earlier. Yeah? And moreover, sometimes we break these things into x, y, z components, or maybe more generally like x1, x2, x3, ... xn. Then we're going to call those the component function. And our goal in geometry is to often not work with these functions as much as possible, because they're somehow not like geometric in nature, right? Like using coordinates is sort of cheating, because if I take my curve and I rotate it, I haven't done anything interesting to the curve, but these functions x, y, z somehow look very different, right? So we're going to try to avoid that as much as we can. Notice like a lot of people in differential geometry class complain about these objects called Christoffel symbols. Those are sort of the byproduct of not ignoring that and trying to do differential geometry using coordinates, and then suddenly you're stuck in like index hell, right? So in my mind, that's oftentimes an indicator that you've done the wrong calculation, but not always. Sometimes you're stuck with it. Okay. Whew. So to go back to the philosophy that I've been trying to lay out to you guys, essentially, when I lay out a curve and I want to do some measurement on it that is about the geometry of the curve, rather than the curve as a function of t, then it needs to be independent to change of parameter. In other words, if I give you or me two different functions gamma that trace out the same object, and then I sort of attach to every point on gamma some measurement, that measurement had better not depend which gamma that I chose. That sentence was poorly phrased, but did we parse it? In other words, like if I trace out the curve in two different fashions, like one of them I drive with constant speed, and the other one, like, you know, one of you guys is driving, you hit the accelerator and it speeds up. That should not affect the calculation that I did. Yeah? And we'll see examples of both of those. Okay, so fantastic. So as an initial example here, let's talk about velocity and acceleration, because that feels like sort of the easiest calculation we might do. Yeah? So, by the way, we're going to continue hiding in this corner because according to the university, there are literally 0 classrooms available on this campus other than this one for this time slot. So that's fun. Okay, so let's say that I have two ways to trace out the same curve. I'm going to have gamma of t, and then I'm going to like make some new guy, which is gamma tilde of t tilde, like that. Okay? And I'm going to be able to relate these two guys because at the end of the day, for every time here, there's some time there which corresponds to the same point. So I'm going to give that function a name. Namely, I'm going to say that t is equal to phi of t tilde. Okay? That makes sense so far? Now, I'm going to make one additional convention here. It's just we're going to work with oriented curves, meaning that my car can't turn around. And the way that I can express that in this language is to say that phi prime, I guess, of t tilde is greater than or equal to 0 for all t tilde. Does that make sense? So we're just going to always drive in the same direction of the curve, but we are allowed to speed up and slow down. Okay. Incidentally, right, so we can say that phi tilde, there's a bunch of different ways to write this. So here's gamma tilde is like this. Phi of t tilde, like that. Yeah? There's one additional piece of notation which you've probably seen before, which is composition. All these things mean the same thing. Okay. Right, so the first thing we might do is we're going to say, okay, let's say that I have a curve like that. There's a curve. See, I drew it with my chalk, so we know it's a curve. And I drive my car along it. So that this guy's my little placeholder for my function gamma. And I want to attach to every point along the curve some interesting geometric property of it. And the first thing that I might think of is to say, aha, here's what I'm going to do. I'm going to take the derivative of gamma with respect to t. That gives me a vector, right? Sometimes it's called velocity. I'm going to attach it to every point. Yeah, so like I'm going to like maybe attach a little tangent vector like that. And the question is that valid in differential geometry? Can I call that a measurement? Spoiler alert, the answer is going to be no. We already intuitively know that, right? Because if I drive down this road 2 times as fast, what happens to the velocity vector? Thank you. Yeah, I'm dying here. It gets twice as big, right? If I drive 2 times faster, the velocity is 2 times as long. So is that like an intrinsic property of this curve? No, it has to do with how I drove along that curve, and that's against the rules. So let's formalize that mathematically. So in particular, let's say that I take gamma tilde and I compute the velocity at time t tilde. Then just by chain rule here, of course, what is this thing? Well, this is really gamma prime at phi of t tilde times phi prime of t tilde. Does that make sense? So notice that there's a problem here, because if I measured this thing by computing velocity from gamma prime, right, this is the quantity I get. If I measured the velocity from gamma, this is the quantity I get. And it's certainly not the case that phi prime has to be 1. And so we know that there's a contradiction here, and this is not a measurement that we can make. It's a perfectly fine thing to do with calculus, but it's not an okay thing to do for differential geometry. Does that distinction make sense? Obviously, we're going to fix this in a second. How are we going to fix this? We're just going to divide this object by its norm, right? And then we're good, because then we've gotten rid of this factor. Okay. So here's an example of a measurement that we made that is not invariant to change of parameter. So it is not a thing that I can attach to points along a curve, because I can come up with two different functions gamma that trace out the same curve and give me two different versions of the same measurement at a point, to summarize. Everybody with me so far? We're a little pedantic, but like we're going to add detail more and more. Yes?
Those gamma tildes on the right-hand side in the first line is gamma.
Almost certainly. I make a lot of mistakes. Which one?
On the right-hand side of the first line,
The right hand, this guy.
yes, gamma composed with phi.
Yes, sorry. Yeah, thank you. That's right, because phi is the thing that maps into the other curve. That's my apologies. Thank you. In fact, I remember the last time I taught this course, it was on this like godforsaken filming thing because of COVID, and I had to film this little segment like 8 times because of all the, it's just easy to get these symbols wrong. The good news is that we're going to do this kind of calculation like twice, and then we're going to stop doing it because it's annoying. Okay. Any other, have I made any other mistakes you guys can help me fix? Everybody's so quiet. Okay, so what did we learn? We learned that essentially, we have to be a little bit careful. Velocity is indeed dependent on choice of parametrization, so it's not a reasonable measurement to make. We're going to skip acceleration. We're going to come back to it in a few minutes. Okay, so what's a measurement you probably learned in calculus class that is invariant to change a parameter? Anybody think of one? Here's an arc length. Yeah, the length of the curve, right? In fact, in some sense, that's like sort of the prototypical thing you do with the curve that is about the curve and not about the function gamma, right? But one thing you might not have done is actually checked that that's the case, right? So let's do that. In particular, in case you forgot from calculus class, here's the formula for the length of the curve from A to B for a parametrized curve, right? So one thing that I might check is, does this definition get messed up if I like chose another gamma that agrees with the same curve, right? That's essentially the kind of thing that I have to keep checking here. Okay, so is it okay if I erase this little calculation because there's probably other mistakes here anyway? Okay. So, wish I were like a foot taller. Okay. So let's say that I have, yes?
Why is the 2 on the bottom again?
Why is the 2 on the bottom? Oh, okay, so this is just notation. This is the 2 norm of a vector. So this is the square root of the sum of the squares of the elements. It's to distinguish from things like the L1 norm, which would be the sum of the absolute values. I think if you're used to just undergrad class, you're probably used to those double bars without the 2 there, and that's perfectly fine. Yeah. In fact, in this class, it'll be pretty rare that we use any norm other than 2 norm. Yeah. Any other questions? This is fantastic. We're thinking critically. Yes?
Is it okay to integrate from A to B if the definition is over an open set, like A comma B?
Yes, and I will let you reason about that at home. But for now, yeah, we can assume like your curve has endpoints if that makes you more comfortable. Either one is fine. Yeah. It turns out because of the limiting definition of an integral, either one is kind of all right. Okay, so here's our length from A to B. And let's say that I apply my length formula to gamma tilde. So in particular, this is going to be maybe the integral from A tilde to B tilde. I'm going to get really tired of writing all these squiggles. Gamma tilde prime T tilde, the 2 norm D T tilde. And here, by the way, I'm going to say that I'm looking at a curve where T is between A and B. T tilde is between, so it's like the same setup as before. A tilde and B tilde, like that. And moreover, I'm going to say T is equal to phi of T. So exactly the same setting that we had, right? So remember, there's basically this thing phi, which is giving me the mapping from one curve to the other. Everybody with me so far? I see some furrowed eyebrows. If you have questions, it's okay. Okay, so let's keep going. So what should I do? So the first thing that I can do, remember I have a formula for this object, which I conveniently just erased. That's my apologies, but we can write it down here. So this is, of course, the same integral from A squiggle to B squiggle of what? Well, we have gamma just by the chain rule, like this, by definition of T tilde, right? And then I need to take care of that factor gamma prime of T tilde D. Right, and this is just by definition. Right, so remember that gamma is the guy that maps from the tilde things to the non-tilde things. Yeah? this guy inputs things that don't have tildes in it, so this whole notation is consistent. We did it right. Okay? And remember, just by convention, we've assumed our car doesn't turn around, so this is a positive number. So this absolute value is irrelevant. Okay, so this is just chain rule. I haven't done anything involving integration yet, but obviously at some point I need to switch from the tilde variable to the non-tilde, yeah. So luckily for us, we're going to use our favorite trick from high school calculus, which we call U substitution, right? Or change of variables, whatever you want to call it. So in particular, we're going to make a variable t, which we're going to say is phi of t tilde. We can do that because phi is sort of injective, right? That's okay. Yeah. So if we want to do our little like AP calculus schematic, what do? You do dt is equal to phi prime of t tilde dt tilde, right? Kind of remember that little change of variables trick that we do? Okay. So what is this integral? This is now the integral from just a to b, right? Because that's our change of variables that we just did. So we have gamma prime. Now we have phi of t tilde, which is exactly t. Notice that this entire expression is exactly our dt there, like that. Well, presto changeo, what do? This is our length operator, right? This is L of gamma, right? With the appropriate choice of endpoints. I guess we should probably be careful about writing that down. Yeah? So notice that this little derivation here is showing exactly the kind of thing that we need to show about every single calculation we want to do in differential geometry. That if I gave some other parameterization of the same object, the measurement I would make would be the same. That's the philosophy that we just did here. Does that make sense? Yes?
What happened to the sign?
We made a convention, which was that the sign of phi is positive. Yeah. You're right. Technically, the calculations we're doing here are for oriented curves. You should be the tiniest bit careful if you want to go back and do all the sign stuff. I'm just being lazy. So technically, when I draw my curves, I suppose I should like stick a little arrow on them. But yeah. All right. Does that make sense to everybody? Fantastic. Okay. So that's great. But you know what would be a giant headache? Would be every single time we do a calculation on a piece of geometry to then have to go back and prove a theorem like this. Because these calculations, like this is the easy one, right? But like we're going to be proposing progressively more complicated measurements to make about a curve, and then to have to go back every single time and prove that your measurement is invariant to choice of parametrization is just a headache. And so we use a little trick in differential geometry, which is we choose a canonical choice of parametrization and then do our measurements in terms of that object. And so long as the parametrization didn't depend, like only depends on the geometry, any measurement we make from that is okay too. So let me be a little more specific about that. I always struggle in intro differential geometry because I feel like there's a lot of things that are actually quite intuitive, but then you say them in words and they sound really yucky. This is one of them. So let's say that I have a curve. One thing that I can do is make a very careful choice of this phi function here to trace out that curve in a very special way, which is parametrization by arc length. By the way, oftentimes I'm lazy and I'm going to use the acronym PBAL, PBAL, which is parametrization by arc length, because it's a mouthful of a phrase to write down. Okay? So what does parametrization by arc length do? It says, okay, I'm going to make a very careful choice of my function gamma here, which is that of all the different ways that I'm going to trace through my differentiable curve, I'm going to choose the one where my car is driving with speed 1. Right? So this is going to become even more important when we talk about curvature of surfaces. So essentially, there's a lot of different ways that you could experience acceleration when you're driving along a curve. This is going to be the main point. So again, remember, we're thinking of gamma as a map from time into position, right? There's two types of acceleration that I can experience. Remember, acceleration is like second derivative, because we know that the first derivative is some positive number. So first one would be the following. Let's say I'm driving along a straight line and I just hit the accelerator on my car. I get pushed back into my seat and I feel a little acceleration that way. Is that acceleration interesting from perspective of geometry? No. On the other hand, as I'm driving along my car, sometimes I have to turn the steering wheel. And just by virtue of turning the steering wheel, I experience acceleration, right? Notice now the acceleration is pushing me on the side. It's not pushing me forward. That acceleration is a byproduct of geometry. It is not a byproduct of my car's engine. Does that make sense? Like, I necessarily have to turn my car in order to keep it from just driving along a straight line. That's the interesting one. Right? And so when we parameterize by arc length, what we're doing is we're purposefully choosing a parametrization gamma of s so that s is like as if I were driving with unit speed. Yeah? So in particular, what do? Well, we have this formula for arc length as a function of t, right? We can certainly invert it, and we just use that as a parameter for our curve. And the formula is here. So here, this is capital S or little s of t. I apologize, I messed up big and small s's here. Right? So this is a function that inputs a parameter t and gives me back s. Yeah? I can invert this thing, right? This is an invertible function. It's increasing. And that thing gives me a map from s's to t's. And this is sort of the canonical way to trace out my curve, right? So at any given base point, I can just choose a gamma of s that traces along driving with unit speed, and you can check quite easily that this is unique up to orientation, right? You can turn your car around, there's only one way to drive with constant speed. That make sense? So here's the thing. I can write any formula I want in terms of the derivative of gamma as a function of s, and that is necessarily a geometric measurement because I derive this parametrization from the shape. It has nothing to do with the choice of t. And so that's the trick in differential geometry, is as long as I do calculus on that object, I'm good. Here's going to be the problem. This is great on curves. Can I do this on surfaces? The answer is going to be no. There's an object called the exponential map, which is close, but it turns out that like if I have any curvature at all, somehow I'm mapping from the plane now instead of a line into like 3D, for example. And well, if there's curvature, there's got to be some distortion. There's no such thing as unit parametrization anymore. But in 1D, we're good. Okay, so this is going to allow us to do some really cool stuff. Is my extremely sophisticated way of putting it. So let's do some examples of this. So first of all, we're going to derive a measurement which looks like the measurement we did before, but now is invariant to choice of parameter, which is the velocity of gamma as a function of s. And again, this is up to orientation. We're going to assume that all our cars are driving in the same direction today. Okay, so. In particular, let's say that I want to compute the velocity of my curve as I drive along. So I have gamma tilde prime of s, right? And let's say that I only have a, I only have the setting that I had before. So like I have some arbitrary parametrization t. Right. So then by our favorite chain rule computation here, what is this thing? This is gamma prime of phi of s, where now phi is this thing that maps from arc length to t, right, that we've drawn before. It's the inverse of this function s here, times phi prime of s. And again, remember that phi, I guess, inverse of s, which is now, I guess, a function of t, is the integral from some fixed t naught that doesn't actually matter to t of gamma prime of t dt. Okay? This is a little weird to define a function by virtue of its inverse, but notice that this is an invertible function, so it's sort of okay. Yeah? Okay, so what is phi prime? Well, the derivative of the inverse of phi is just the thing inside of the integral, right? That's the fundamental theorem of calculus. Right? So the derivative of this function phi inverse is just this object here. So what is the derivative of its inverse? Remember the inverse function theorem? The reciprocal. That's right. So in particular, this thing is gamma prime of phi of s divided by mod gamma prime phi of s. Yeah? This is a unit length vector. Yeah? So essentially, what did we show? We showed that like if I'm driving along my curve, yeah, and I want to attach an interesting measurement to every point, I can't attach the velocity of my car. I can sense that as I drive, but it's not geometric. There's like other information encoded there. However, if I take my velocity and I divide it by its length, so I make a unit vector, I call that t for tangent, this object is canonical, at least up to sign. Again, we're orienting our curve today. We're giving it a forward direction. That make sense? And we got that because essentially the inverse function theorem here. Okay, so this is our first example of a local measurement of a curve that is perfectly valid from a differential geometry perspective. Now, the question is, can we do some more interesting stuff with that? The answer is going to be obviously yes. Now, first of all, we're in the plane here, so there's a lot of nice math that we can do. And we might want to make kind of a complete picture, so let's do that. So in the plane is really nice. just fun fact. One thing that I can do is I can say, okay, so we're going to call this object T of S, okay? And in general, what do I know about unit vectors in the plane? They just trace out a circle, right? And circles have angles. So one thing that I could do is write this thing in coordinates. I'm gonna break the rules just a little bit, just a little, I promise. And I can say, okay, well, what is T of S? I can define a function theta of S so that T of S is really equal to cosine theta times the first coordinate plus sine theta of S times the second coordinate. I can only do this in the plane, yeah? This is unambiguous, so theta here is like just the heading of my car. Does that make sense? Now, this function is a little annoying to work with. If I take my curve and I rotate it, then this function changes, but it does exist, yeah? Okay, so one thing that I can do is, like, let's say that I want to know all the derivatives of my curve. The first thing that I might try to do is differentiate t. This is going to lead to like the canonical formula we're going to be playing with a lot in this class. Okay, so I might ask, what is the rate of change of the tangent vector to my curve? And let's think about that again in terms of physics, right? So this is like the second derivative of my curve, kind of, but now with the assumption that I'm driving along it in a car that's driving with unit speed. So first of all, if my car is driving along unit speed and my curve is a straight line, what's going to be the second derivative? 0, right? Because the tangent is just constant, yeah? Notice that corresponds to having 0 curvature in my curve. It also corresponds to theta here just being constant. Like I take my steering wheel, I point it at 0, and I just keep going, yeah? What happens if my curve is bendy? Well, now the second derivative of this parametrization by arc length is interesting, right? It's a non-zero quantity, yeah? What does that correspond to? Remember, second derivative is like force, right? So I have a car that's driving along this curve, and it's experiencing force now just due to the geometry, not due to hitting on the accelerator, right? And that force is going to be like curvature, right? In the sense that the tighter that my car is turning, the more force that I'm feeling, right? When I'm driving along a straight line, I'm not feeling anything at all. Does that make sense? Cool. So let's do that calculation. So in particular, let's write t prime of s. Now what's the derivative of cosine? If you trust my formula sheet a couple days ago, you would get it wrong. That's my apologies, but I fixed it. All right, on 3. 1, 2, 3. Derivative of cosine. Thank you. Minus sine theta. But I have to be careful. There's a chain rule because this is a function of s, right? We have a theta prime of s. And now we have minus sine theta of s E1 plus cosine theta of s E2. Like that. Make sense? So let's stare at this formula for a minute. Notice that this has components cosine, sine. This has components minus sine, cosine. So what is this picture? These are, if you take the dot product of these vectors, what do you get? 0, right? So what is the schematic that we have? Our car is driving along. The tangent is this way. The normal, oh gosh, I gave it away. The second derivative is orthogonal to the tangent, like that. Right? So that's the force that you're feeling when you drive along your car. And notice conveniently that it kind of divides up into like the forward force when I hit the acceleration and the sideway force, which has to do with curvature. Yeah? But there's this pesky factor here, theta prime. We're going to give that a name. We're going to call that k. And k stands for curvature. So now we have a good interpretation of what curvature means. It is the rate at which the heading of my car changes as I drive along the curve. Does that make sense? Fantastic. So if we want to be slick about it, let's define a matrix, J. We'll call J 0, minus 1, 1, 0. So this is like rotation in the plane. Then what did we just show? We showed that T prime is really equal to some curvature factor times J times the unit tangent, like that. That make sense? Nods, acknowledgement, something, help your instructor here? Cool. This is a cool story, right? This is really tidy. Like, math is nice. So here's a schematic of what this looks like, right? So we have a curve that's parametrized by arc length. It has this unit tangent necessarily, just by parametrizing by arc length. Then when we take the second derivative, we just get a rotated version of the tangent. T prime. And ignore that very last formula on the bottom right. That makes no sense. My apologies. I will fix it on the slide. Everything except this last equality. This was a typo late at night last night. Yes?
Doesn't J rotate counterclockwise?
Probably. I always get these things wrong. J rotates 90 degrees in whatever direction it makes sense. Actually, from this picture, I mean, you expect curvature to point the direction of the curviness of the curve. So from here, you can see counterclockwise. Yes?
K negative then, or?
It depends on the orientation of your curve. Everything in this course is going to be up to sign. Okay. Other intelligent questions that I'm going to evade? Anything else I can answer? Yes?
I can ask a stupid question.
Please do.
If we choose the sign so that J has a negative, why didn't we choose it to be cosine minus sign? Because then J would just be wholly x.
We could, yeah, I mean, we could choose whatever sign we want to. This is convention at this point. Notice in 3D, we're not going to be able to do either one of these things. So we'll come back to that in a minute. Yeah. But you're right, like, orientation here does matter a little bit, but only mildly. All right, any other questions? So what do we do here? We computed this value curvature. Notice that, like, somehow the calculation that we've done here is a bit frustrating. Are there questions here, folks? Okay. Notice that the calculation that we've done so far is a little annoying. Like, I use coordinates, and that's sort of cheating a little bit. And we'd like to kind of avoid that. But we can do a little bit more to complete our picture here, which is to take the derivative of the normal vector and see what we get, which in 2D is particularly easy. So let's do that. So what is n prime of s? Well, that's the same thing as j times t prime of s, right? Because j is constant. Yeah? We have a formula for t prime, right? This is equal to kappa of s. We have this j. We get another j from the t prime times t of s, like that. Right? So one of these two j's is that j, and the other of the two j's comes from this formula here. That makes sense? What's t squared? Well, if I rotate twice in the plane, I turn backward. So it's just minus 1. So this is minus k of s, t of s. So notice that there's like order in the universe. This is a really tidy set of formulas, right? What did I show? I differentiate the tangent. I get this thing 90 degrees away from the tangent. We call the normal. I differentiate the normal. I get a multiple of the tangent again. And they both have the same coefficient kappa up to sine. Yeah? Isn't that tidy? This is a great example of sort of a trick that we do in differential geometry. Namely, if we ask, like, how might I describe a curve without coordinate system, right? Like, let's say I didn't have access to that x or y. Well, a natural coordinate system I could choose would be t and n. But if I do that, then I have to do weird stuff. Like, if I want to differentiate t, the only basis I have for doing that is in the t basis again. So I end up with like formulas like these ones, where I'm differentiating quantities and then projecting it back onto the thing that I just differentiated. Right? It's kind of funny that way. So in particular, we have this very tidy formula here, sort of turtles all the way down. We can just keep reusing t and n to differentiate as many times as we want. So this gives us a way to differentiate tangent and normal in a way that just keeps rotating 90 degrees. Yeah. Sometimes this is called the Frenet frame or the Frenet formula, although usually that phrase refers to the 3D case, which we will do momentarily, I think. Yes. Any questions so far? I hope not, because I'm running late. Okay. Fantastic. Notice, by the way, if I take 1 over k, right, that number now is sort of infinity when I'm flat, and as my curve gets more bendy, it gets smaller, right, because it flipped. The picture to have in mind is that, like, this is sort of the radius of a little circle that's just barely touching your curve. Does that make sense? Anybody know the name of this circle? Some good differential geometry trivia here? Anna? It's the osculating circle. Does anybody know what that means? I wore the right outfit for this today. Yes? Yeah, it's kissing. It's the only time I've ever gotten to give this lecture on Valentine's Day. This is very exciting for me. So in any event, this is called the osculating circle because it just kisses the curve, just barely, with the highest degree of contact you can have. Okay, so that's our 2D picture. But here's the kind of theorem that we usually prove about this 2D picture. So what have we done so far? We said, like, given a curve, I can give you back gamma, or kappa rather, and it tells me something interesting about my curve. I could also ask the inverse of that question, right? Like, let's say I give you a function kappa. Are there like different curves that have the same curvature kappa? Right? We have not answered that question. Spoiler alert, the answer is no. You can see it on the slide here. Namely, there's the fundamental theorem of the local theory of plane curves, which says that if I know kappa, then I know my curve up to a rigid motion. This is going to be one of these annoying mathematical things where somehow like the statement of the theorem is actually kind of longer than its name or its proof. But it's very easy to check this fact. And the way that we check it is basically by inverting the calculation that we just did. Right? So essentially, here's what we can do. We have to define we have to sort of solve two problems in one. So the first one is the following. So let's say that we're given a differentiable function kappa of s, right? Then we need to show that there exists some curve with this curvature kappa. I see your hand. Then what we want is to show that there exists gamma of s with curvature kappa. So in other words, there's not like some weird function that doesn't define a curve. Right? We haven't technically shown that. Right? We've only shown how to go from curvature, or from curves to curvature, not the other way around. The other thing we have to do is if two curves have the same curvature kappa of s, then they're the same up to rigid motion. So this is, when I say rigid motion, I mean rotation and translation. Yes, your question?
Doesn't all that have to be non-zero?
No, you can have zero curvature. That corresponds to a straight line.
Yeah, but how do you know how far it's gone while it's...
Because you're driving with unit arc length, with unit length, with unit speed. It's not an assumption, it's a definition. I'll let you go back and double check that. Yeah. Okay. So these are the two things that we have to prove to like sort of more formally establish this theorem that's on the screen here. Yeah? So first, given a function kappa, there exists a curve with curvature kappa. Second, if I have another curve with the same curvature, it's actually the same curve. Okay. So how do we prove this? Well, for one, so it's almost identical to what we've already written down. We're just going to basically play our tape in reverse, right? So in particular, let's say we take some S0 in the interval where kappa is defined. So maybe we'll call that A, B, like that. And we're going to define a function, theta of S, to be the integral from S0 to S of, of kappa. Because remember that, like, we're trying to reverse engineer a curve from the curvature. So one thing we might do is first reverse engineer that theta. Remember that we got kappa as the derivative of theta. So one thing we could do is just reverse that. Now we have theta. Does that make sense? So now, given theta, I can reverse engineer the unit tangent, right? So I could then make another, and now these are definitions, right? Because I'm going from kappa to my curve. I could say, aha, so this thing is maybe cosine theta of s E1 plus sine theta of s E2. Yeah, these are all definitions. And how do I get my curve? We're going to integrate again, right? Because remember, the tangent is the derivative of my curve. So I can say, okay, I could define gamma of s to be the integral from s naught to s of t of s ds. I'll put bars to disambiguate. And one thing you can do is very easily check that this thing has curvature kappa. In fact, it's almost just by definition, right? This proof feels like a tautology, but it's not. Yes?
Does kappa be like differentiable or interval?
Well, I guess a differentiable is certainly sufficient. Well, I suppose differentiability implies integrability in this case. So whatever, it doesn't really matter. Yeah. Okay, does that make sense? So like essentially, given a function kappa, there always exists a curve with that curvature kappa, and we can do that by just integrating the function back, like just reversing the definitions we already had. Now, the other thing we have to do is to make sure there's not like some completely different wiggly curve that has the same kappa, in which case I need to make a second measurement. Does that make sense? Like, it wouldn't be enough to just attach one number to every point and then reconstruct the curve. So this one's a little bit trickier. The course notes do this in more detail. I'm just going to sketch it here because we're low on time, and I'd prefer to do the 3D case. So in particular, see, it's not fair. The last time I taught this class, I got to do redos when I was low on time, but I don't get to do that in this format. Okay. Right, so now, what do we need to do? So this is for fact number 2. We're going to take a second curve, which maybe we'll call gamma bar of S, this way, with curvature kappa of S. Right? We want to show that gamma bar and gamma are basically the same, right? And when I say the same here, I mean up to rigid motion, meaning I can translate and I can rotate. Does that make sense? Okay. So what we're going to do is we can show very easily, in fact we already have, so that both of them satisfy the same ODE. Remember the ODE stands for ordinary differential equation. And in particular, it's the following. It's d over ds of gamma Tn equals something in terms of gamma Tn. So what's the derivative of gamma with respect to S? It rhymes with P. T. Thank you. So in this notation, I can write it like that, right? What's the derivative of T with respect to curvature? Kappa n. We got there, right? So that would be like that, right? 0, 0. What's the derivative of n with respect to arc length? Thank you. 0 minus kappa 0, where these are all thought of as functions of S. So they both satisfy the same differential equation. Yeah, and essentially what we're not going to write down because it's a little wordy is that we could take gamma prime and we could like choose an S naught, so like just choose some point along the curve, and we could translate our curve and rotate it so that they have the same base point and the same tangent at one point in time, right? So I have like this curve, then I have some other version of basically the same curve, right? And we know that they have the same curvature function. So like at this corresponding pair of points, they have the same curvature. They're not the same curve. But I could translate this curve, like I could move it over here, and I could rotate it so that their tangents align. I can do that at one point in time. I don't get to do that at more than one point in time, but I do get to like move this guy around in the plane. Yeah? Well, at that point, what ends up happening? They both satisfy the same differential equation. In particular, gamma does. They both have the same initial conditions at that point, right? They have the same tangent at normal at time 0. So by existence and uniqueness of ODE, you're done. Yeah, they're actually the same curve. So the course notes do that in a little more detail. But essentially the main takeaway here is that there's a very simple differential equation argument that shows that like curvature completely determines a curve in the plane. Notice that last part is really critical. In particular, that we made a lot of arguments using that little J matrix. And that J matrix is not going to exist in 3D. This is very specific to 2D. Okay? So now, sort of, if we step back 100 feet, what did we learn? We learned that, like, essentially the only thing there is to know about curvature, the only thing there is to know about a curve is this curvature, right? Like, once we know it's curvature, we know everything there is to know about a piece of geometry. That's what it's sort of saying. Yeah?
So like the summary of what we did here is we chose a coordinate system attached to the curve. Therefore, when we change that coordinate system, it doesn't matter.
Yeah, basically, yeah. If you're a physicist, you sort of think of it like something inertial frame, you know, like, I don't know. I'm not used to thinking that way, but yeah. Mm-hmm.
Doesn't the second part also prove the first part? Like if you wanted to, you could have just written this differential equation.
Yeah, I guess that's right. I guess you could have used it. That's right. Then you're relying on like kind of heavy-duty machinery for a pretty simple fact, but yeah. Yeah, what is this, the Picard-Lindelhoff theorem or whatever? But yeah, you can also just do it directly. I think this is more useful. In fact, there's a nice picture for what's going on here. Essentially, you know, we can reconstruct, there are all these different relationships between curvature, turning angle, tangent, And there's this map from the surface into or the curve into the unit circle. This thing is sometimes called the Gauss map, by the way, which is really what's determining curvature here. Okay. Oops, sorry. Yeah, so the Gauss map, to be precise, actually usually we think of it as the normal vector. For curves, it actually doesn't matter. Okay. One additional measurement we might make about a curve, which is kind of a fun one to think about, is something called the winding number. This is an important one that actually shows up in computer graphics applications. This really does depend on our curve being connected and oriented, to go back to some questions before. But one thing that I could do is look at the integral of curvature from A to B of a curve, and let's say that my curve is closed. Okay? That make sense? Now, remember, curvature was the derivative of this angle theta, right, where you keep going back and forth between theta and curvature, right? So let's say that my curve is closed and differentiable, right? Meaning that at time A and time B, I'm at the same place, and moreover, I have the same tangent. That make sense? Then what do I know about the relationship between theta at time A and theta at time B? Well, they both point the same way, right? I know you guys know, you're killing me. If I have two angles, like I have two angles that determine the same direction in the plane, then those angles are the same up to a multiple of 2 pi, right? So they're not necessarily the same, but they are the same up to 2 pi. So that multiple of 2 pi, notice that that's exactly this number here. It's called the winding number, and if you think about it, it's like the number of times that the curve turns around itself, yeah? This is our very first example of what we will call a topological invariant. Isn't that fun? In particular, if I take this curve and I deform it in a nice smooth way, does the winding number change? No, it just stays the same, an integer, right? Notice this also kind of implies something a little weird about differentiable curves, right? Can I take this curve and smoothly deform it into this one in a sequence of smooth curves? No, right? Because then the winding number at some point is going to experience a discontinuity, but this thing is necessarily a smooth function the way I've kind of written it down, right? So what it means is like there are like these kind of interesting homotopy classes, which is a fancy way of saying like I take a curve and I yank on it and I pull it around and so on. I can certainly deform one of these curves into the other, but at some point when I do that, it's gonna develop a kink. Yes?
So if we're even considering curves like the third and fourth one, then we're using the parametrized definition of curve?
This is true, yeah. This is parametrized, connected, closed, differentiable curves. Yeah. Although this particular definition, you can work out a version of winding number that like accounts for corners. And then we're actually going to do that in the next lecture because we're going to talk about polygons. Yeah. Or maybe in 2 lectures. I'm moving slowly. We might have an addendum to this one today. Okay, fantastic. So that's the whole story for 2D. Like we've done every possible thing you could do to a 2D curve. The obvious next question is, what do you do in 3D? And the story is very similar, but a little more annoying. So we're going to start to develop the story today. We've got about 10 minutes, and we're going to see how far we get. And that's going to be our goal for the rest of lecture, is to develop a similar set of formulas to the ones we just wrote down. I think we can do it in 10 minutes. Do you think so? I think so. So, now we're going to think of a curve as, being mapped from a function on a line into 3D instead of 2D. Okay? Just an FYI, folks, I don't know if it's the acoustics of this room, but you're a lot louder than you think you are. Okay, so what we're going to do is we're first going to prove some useful propositions, and then we're going to go back and we're going to apply those to deriving this nice set of Frenet-Serre formulas, okay? So here's going to be our proposition. It's going to have 2 parts. 1, suppose v of t, which is going to be some smooth function into Rn, satisfies that the norm of v of t is identically 1. Okay? So in other words, I've got like this time-varying unit vector. Okay? Then v prime of t dot v of t is equal to 0. You almost can already see where the proof is. This is a one-liner. Okay? And then similarly, if v of t dot w of t is 0, so now I have a time-varying kind of pair of orthogonal vectors, okay? Then v prime of t dot w of t is equal to minus w prime of t dot v of t. These are both just the product rule, but it's important to call these out because it turns out this is sort of the basis of a million formulas in differential geometry. When I was writing the course notes, I kind of went back and added this because it's convenient. Okay, so let's prove this really quickly. So 1, if we differentiate both sides, right? So 0 is obviously equal to the derivative of d over dt of 1. Yeah. But now I'm going to square both sides for convenience. This is the same thing as d over dt of the norm of v squared, right? Just by assumption. This is the same as v dot product v, so this is really 2v dot v prime by product rule, and now we're done. Yeah? Okay. My undergrad, like, intro to proof professor took off points if we put check marks at the end of proofs. He said there's, like, no such thing as a victory mark. So I make a point of it now. Okay. So second of all, we're going to do exactly the same argument here. So if I take d over dt of 0, well, what is that? That's the same as d over dt of v dot w, which is v prime dot w plus v dot w prime. Yeah. And this expression, if I rearrange it, is exactly the thing we wanted to prove. Okay, so these are easy facts. This is nothing surprising, but they're just things that get used over and over and over again. So we're gonna just call them out for what they are. Cool? Okay, team. So our final task here, no big deal, is to derive our moving frame on a 3D curve. And it's going to look like a very similar story for the first derivative, and then we're going to have to take another derivative because now we're in 3D. So our curves can do two things. Like having a one-dimensional steering wheel isn't enough to draw a curve in 3D. That's the basic point. So I have a 1D steering wheel to move on the plane, and I'm going to have like another steering wheel that like points my car up away from the plane. That thing's going to be called torsion. Okay? So what are we going to do? We're going to take a curve gamma parametrized by arc length in 3D, and we're going to derive a relevant frame. Okay? And I think we can do it in 5 minutes or maybe a little extra time, but I blame the class before us. Okay. Ugh. So here's going to be our calculation as as follows. So let's take gamma of s to be parametrized by arc length. Okay? So, we're going to assume, of course, that gamma prime is not equal to 0. That's our sort of basic setup for all of these problems. Okay. So first, we're just going to make a definition. We're going to say t of s is going to be equal to gamma prime of s. We can certainly make that definition. And we know that essentially gamma being parametrized by arc length, what we showed earlier in the lecture is that that implies that t is a unit vector. Okay? So far, like, what is our picture? We have a curve in 3D now. It's in 3D because I drew the axes. Okay? We're at a point and we have a tangent vector. There's t. It's much harder to draw the other two, but I can draw this one. Okay, so now, how do you think we're going to get the next vector in our basis? Cross product. With who and what?
T and N.
T, what's n?
Normal.
Yeah, how do I define that?
Orthogonal T.
But there's many orthogonal. There's a whole plane now, right? I'm in 3D. Take the derivative. Yeah, that's right. So, in particular, we are going to do the following. So, we now have a proposition that we can use, namely proposition 1. What does proposition 1 say? It says, okay, so t is a unit vector. So when I take the derivative, it's going to be some vector which is orthogonal to t. Yeah? By the way, here we're going to assume that the derivative is non-zero for now, and we're going to come back to the case where I have a straight line. It turns out that straight lines are actually the problematic case for this theory, which is an interesting kind of observation. But for now, by proposition 1, I can say that there exists kappa and n so that t prime is equal to kappa n. right? Why is that? Well, essentially we know that t prime is some vector that is orthogonal to t. So I'm going to call the unit vector in that direction n, and its norm kappa. Notice in this theory, to go back to a question from before, we maybe make kappa always positive just by convention here, right? That makes sense because it turns out the sign of curvature only makes sense in the plane, because otherwise in 3D, if you look at the curve from the bottom or the top, it's kind of curving clockwise or counterclockwise. There's no orientation anymore. So we'll just make the convention that kappa is positive here. Notice when there's a straight line, there's an ambiguity here because kappa is 0, so I can put any unit vector I want there. So maybe by convention, I just choose something that's orthogonal to t. Yes?
When you say plane, you mean the plane that's defined by t and n at the point we're considering?
Well, there's a plane which is everything that's perpendicular to t, right? So the proposition 1 tells me that the derivative of t is something perpendicular to t, right? We're just going to give that a name n.
Okay.
And usually it's unique, but, oh, sorry.
The plane is changing as we go around.
That's right. Yeah, yeah. So everything I write here is going to be a function of s. I'm just rushing because I'm low on time. I'm sorry about that. Feel free to stop me anytime, really. Okay. Everybody with me so far? So far this is identical to 2D. All we said is there's something perpendicular to t that gives derivative with respect to s, and we're going to give the norm of that a name. It's k, kappa. But now we're not done, because we want to differentiate again. But notice that I no longer have that matrix J that relates these things, because they're in 3D. Like there's not a single 90-degree rotation matrix. You can rotate 90 degrees about a lot of different axes, yeah? So instead, I got to do some annoying math. Okay. So, right, so by the way, let's just memorialize this. We know that the norm of n is 1, and we know that n dot t is 0. So our picture so far is that. These are 90 degrees from each other. Now, we had a fantastic suggestion before. We have two vectors. We want a third one, which is orthogonal to them, so that we get an orthonormal basis. What are we going to do? Cross product. That's right. So let's define an object. We're going to call it the binormal B, and it's going to be the cross product T cross N. Okay? So remember your right-hand rule here. So like here, the binormal is like that. It's hard to draw on the board. Okay? So now here's what we want to do. We want the derivative of T, the derivative of N, and the derivative of B. And we can write it in what basis? The T and B basis, because that's the only one I have access to. And what we're going to see is there's really, really tidy formulas for doing that. Notice that I already have the derivative of T in the T and B basis. It's right there. Yeah? Okay. So we know that T, N, and B form an orthonormal basis for R3, meaning that they're three perpendicular unit length vectors. Yeah? So what are we going to do? Well, that means that for all vectors v in R3, I have the following formula. I can take v and I can project it onto that basis. I can write v equal to v dot t times t plus v dot n times n plus v dot b times b. Do you see what I did there? Like these are like the coefficients of v in the T and B basis. This is just true. This is a linear algebra fact. So nods, acknowledgement. Yes, Justin, I understand this. I'm very excited about the Frenet formulas. Thank you. Okay. So remember my job here. I have to differentiate a bunch of stuff. We've already differentiated this guy. Let's differentiate, which one do we do next? Let's do n. Okay? So in particular, what is n prime? Well, it's really n prime dot t times t plus n prime dot n times n plus n prime dot b times b. Yeah? This feels kind of tautological, but it's true. It's just a weird thing to write down. Does that make sense? So, can we simplify this at all? First of all, remember that n is a unit vector. So what is n prime dot n? Yeah, this is proposition 1. Yeah? So this thing is 0. Okay. What else can we do? Well, we're just going to give this thing a name, by the way. We're just going to call that tau, because we don't know what to do with it. So we're going to call it tau. But let's look at this quantity over here, n prime dot t. Well, conveniently, we have another proposition we haven't used yet. What is that? So what is this equal to? Let's try again. What is this equal to? Yeah, well, now we're going to use proposition 2, right? Because t and n are orthogonal to each other. So this is the same as minus t dot n, oops, t prime dot n. Cool? Well, we have a formula for t prime. It's kappa n. So what is this thing? Minus kappa. That's right. So we just showed that n prime is minus kappa times t plus tau, where we just define tau to be the coefficient, times the binormal. We're almost done, I promise. I know you're all looking at your watches. I don't care. Okay? So, what is our last little homework assignment here? What was that? That's right. Take b prime. What are we going to do? Exactly the same formula again. Yeah? So now, because now, like, notice we're like gathering more and more information, and then we're just using it. So, in particular, I'll use the bottom board. I'm getting confident that we're almost done. B prime is equal to b prime dot t times t plus b prime dot n times n plus b prime dot b times b. Cool? Okay. What's this one? 0 by proposition 1, because b is a unit vector, right? It's the cross product of two unit vectors. Okay. What about this guy? This is a little bit more annoying. We have to think about it a little carefully. So let's apply proposition 2 to it. So in particular, this is the same as minus b dot t prime. Yeah? What is t prime? It's kappa times n, right? So this is minus kappa b dot n. What's b dot n? On 3. 1, 2, 3. Yay, 0. That's right. Now we're cooking with gas. I'm told that phrase is propaganda. But that's okay. So right. So we're almost there. So what is this this thing? So finally, oops, I've kind of I've cornered myself. Okay. So b prime dot n. Well, let's apply the same proposition like for the millionth time. This is the same as minus b dot n prime. Right? We have a formula for n prime. So this is minus b dot minus kappa t plus tau b. Yeah? What is b dot t? Everybody, what's b dot t? 0. Leticia, what's b dot t? 0. Thank you. So this first term is 0. What is b dot b? 1. Okay. So this entire thing is minus tau. So what did we show? We showed that b prime is really equal to minus tau times n. I said minus, but I didn't write it. There we go. So in a very hurried fashion, we derived exactly the formula that's on the screen here, I hope. Yes, okay, good, we did it right. Do you guys see that? So the derivative of the tangent is kappa times the normal. Derivative of the normal is minus kappa times the tangent plus tau times the binormal. The derivative of the binormal is minus tau times the normal. And this is sort of the analogy of the formula we had on the previous slide. One theorem that we are not going to prove in class, but actually isn't particularly hard to prove, it's just annoying, is exactly the same theorem that we had before, namely the fundamental theorem of the local theory of space curves, which says that if I have tau and kappa, then I can reconstruct my curve. As we kind of observed before, you can basically do that with an ODE argument. Yes? That's, so kappa can be 0. That's a straight line. That's actually okay. You just have to be a little bit careful actually going in this direction, because now it's not obvious what n is anymore. But the other direction is actually okay. Yeah?
Did you actually prove the couple with
Yes. We'll chat about that later. One more slide, I promise. You're all packing your bags. You're killing me. Come on, this is exciting. It's curves. The question I always get at the end of the lecture here, which I'm sure I would today because you guys are a pretty inquisitive bunch, which is fantastic. Like, so we just did a 2D picture and a 3D picture. The obvious next question is like, what about 7D? Like what happens then? You actually do get something interesting. So this comes from, this is sometimes called the Generalized Frenet frame, which is just sort of the analogous formula for like higher dimensional objects. So it turns out with every dimension that I add to the ambient space around my curve, I need another function, right? Like I started with just curvature, then I had curvature and torsion. Then in 4 dimensions, I'll need curvature, torsion, and a third thing. And kind of something that's not obvious that I'll let you check at home using kind of similar math is you get this really interesting relationship. You get this matrix where the off-diagonal elements are the non-zeros and everything else is 0. This is not obvious from this formula. And this construction is basically following Gram-Schmidt. Like if you look at what we've done here, you can go back and kind of convince yourself it's the same thing. The reason we don't do this in detail in this course is I've never found a good application for it. One kind of challenge I always set out to our graduate students or anybody in this class really is like, why would I want the Frenet frame in like dimension bigger than 3? We'll see examples on your homework where 3D is useful. And the answer is I don't know. There's like really interesting notion of curvature here that's hard to think about. All right, folks. Well, it was a bit of a race to the finish line, but we have managed to finish continuous curves today. When we come back, we're going to do exactly the same story, but in 3D, or rather, but for polygonal curves instead of for smooth ones. And then we're going to show that these two theories kind of move in parallel to each other. So with that, have a lovely Tuesday, and I'll see you soon. Happy Valentine's Day. Stop recording.